Hi everyone, thanks for tuning in to our last Ask A Prof live stream of the summer. We're really excited and we hope you guys are too. So my name is Tess, I'm one of the Active Minds coordinators and I'm going to be your host today. And before we get started, I'd like to acknowledge that we're on the unceded traditional territory of the Lheidli First Nations, and we'd like to thank them for allowing us to work, learn, and play on their territories. I would also like to thank our mastermind presenting sponsor, the BC Oil and Gas Commission, as well as our other amazing sponsors, Radloff, New Gold, Triton, RBC, and Michael Reed Law Corporation. So today I'm joined by our guest, Dr. Todd Whitcombe, who is a member of the chemistry department here at UNBC. He will be ending our summer off with a big bang and doing some cool chemical reactions and scientific magic tricks. So when we're done, we'll finish off with a Q&A, and if you have any questions, feel free to ask them in the live chat, submit them in the comment section, and we will answer them at the end. So I guess we'll get started. Dr. Whitcombe, take it away.
Thanks, Tess. So yes, my name is Dr. Todd Whitcombe, and I'm the chair of the chemistry department here, and we're going to do what is called a chemistry magic show. There really isn't actually any magic associated with this. It's more about doing some chemistry science experiments, and hopefully they'll give you a little bit of fun and enjoy it. And yes, we're going to try and end the whole thing with a big bang at the end, so we'll see how that goes. But before we do that, I'm going to introduce my able-bodied assistant here. Beth Gentleman is going to help me out today, so she'll be the other person you'll be seeing on camera. And we're going to have some fun, right?
Yes, we are.
Okay, so I wanted to start off today. This is my magic igniter. It gets nice and hot at the end when I press the magic button. And I'm going to show you what happens when you just pop an ordinary balloon because, well, this is physics, right? Physics, it goes bang like that. And nobody's really too worried about that. Nobody's really too afraid of that. I didn't scare anybody here? No? Okay. On the other hand, if I take this balloon here and we put it in play, and actually give me back those scissors because I don't want this to float away. Floating away would be a bad thing. For those of you not in Prince George, it's actually raining up at the university right now, so our table's wet, so make interesting science experiments. But anyways, once again, I'm going to press the magic button on the igniter. The igniter is going to get nice and hot, and I'm now going to scare everybody because it's going to go boom. What you guys can't see, because the camera's pointing this way, is there's a whole bunch of people back here who all went, "Ugh." So we blew it up. I blew up something. I blew up hydrogen. Hydrogen is a flammable gas. What I actually made was water. I made a little bit more rain, actually, if you really want to get technical about it. So by blowing up the hydrogen in the balloon, I actually made the hydrogen react with the oxygen in the air, and that reaction produced the fire and the flame that you saw. Now, if you were watching really carefully, and we're going to do it again in a moment, so you can watch really carefully, right in the heart of this balloon, it stays sort of brown. And the reason is it's a reaction between hydrogen and oxygen that makes the explosion, makes the flame, and produces the noise. And since this balloon is filled with hydrogen, there's no oxygen inside, and there's only oxygen out here. So the hydrogen has to get out of the balloon and move outwards. And so if you watch very carefully, the middle of the flame ball that you'll see is actually not on fire. Now that doesn't mean I could stick my hand in there and not burn, because, well, I'd have to go through all the flame that's around it, but it does tell you sort of what's happening in terms of the gases mixing. And we'll give it another try. Hey guys.
As far as we can go.
Are you guys ready?
Whoa!
You see that one? Yes? Good. Okay. So we started off with a bang today, and we will finish with a bang. But before we get there, this is the...
Yeah, this is the slime.
You cannot do a chemistry magic show without making slime. Now, I believe you guys have all gotten a chance to make slime. You've had it in your kits this summer, but the slime you made was using white glue. We're going to do this a little bit differently. I have a beaker. Everybody should have beakers, right? And I'm going to pour into that beaker some sodium borate. When you guys did it, you were using white glue and contact lens cleaning solution. The cleaning solution in contact lens contains borate or boric acid, and is designed to clean the solution. Borate also shows up in laundry detergents and various places like that, so it's good for cleaning stuff. The other compound I have, a little bit different from what you guys used. What you were using is something called, well, within the glue, there's something called polyvinyl acetate. And that's what makes the glue gluey, but it also makes it opaque, so that it's white and you can't see through it. What I have is a slightly different version of that. It's called polyvinyl alcohol. And the fun part about polyvinyl alcohol is if I mix this correctly, and I stir it all up, where'd my stirring rod go? There we go. What I get is, instead of the sort of opaque slime that you guys were making, I get something that's much more fun because it's clear and it just looks really, 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 really gooey. And you can have a lot of fun with this. Not the least of which is that when you go to a party, you walk with some in your hand, you walk in and go, "Hachoo!" Oops. Somebody want to shake my hand? Tess, you want to shake my hand now?
Yeah, sure.
Come on, shake my hand. Tess is going to come in and shake my hand now.
Okay.
Doesn't that feel good?
Yeah, it feels
Here you
good.
go. You can take that with you.
Oh, thank you.
You got slime.
So you can see we get a very different, a very gelatinous form of slime. It's clear. You can take some food coloring if you like, and we can make it go, what color do we want? Blue?
Yeah, let's go for blue.
We're going for blue today. And you can add some
Lovely sprinkles.
sprinkles,
And add some pizzazz in there.
jazz it up,
Just a little bit
and stir it like crazy.
until we get a nice mix in there.
And you get some nice blue slime now, and you can easily color it, and it's great fun to play with. And this stuff here, this lasts a lot longer than the white, the glue made material. This will last a couple of years in your refrigerator. The glue-based ones, because that glue has all sorts of other things in it, tend to go moldy very quickly. So you don't want to keep them around for a long period of time. But now we have some bedazzled slime. Does anybody else want? Anybody want some slime? Do you want some bedazzled slime here?
No takers. Oh, here we go.
Here we go. So just hold your hand out, and there you go.
I get all of it?
That's all for you.
Thank you.
Some bedazzled slime. Like I said, you can't do a chemistry magic show without making slime, so we're going to switch over in themes today. What we're really talking about today is gas. And gases and the liquids they can turn into. So, and you may have noticed over here I have a steaming pot here. This is filled with liquid nitrogen, and we're going to play around with that in a few minutes and then do some experiments with that. But before that, I thought we'd do another really interesting little experiment. We all know the atmosphere is made up of nitrogen and oxygen. It's about 80% nitrogen, about 20% oxygen. There's about 1% that's argon, which is a gas used in light bulbs and all sorts of light bulbs, and it's used by industry a bit. A little tiny bit of it is carbon dioxide. I mean, the actual carbon dioxide content in the atmosphere is like 0.04%. Has a big effect, but it's not very much. But to show you that there is really oxygen in air, what I have in here is a container with air in it and an indicator below here. And if I shake it up, you'll notice that it turns green. And that's because the oxygen gets inside and causes the chemical reaction to happen. As the oxygen inside in the air, inside that got into the water, reacts, it turns to the red color, and eventually it'll turn back to a nice yellow color. And if the world of science wasn't the way it is, that would have happened. As I said, it turns back to a nice yellow color, but instead it's going to hang on for just an extra few seconds or two until it eventually gets back to yellow. But I can keep doing this. I can shake it up again, get a little bit more oxygen in there, get another green color, and it'll go back to red and eventually back to yellow. So what we're doing there is we're dissolving the gas into the water, and then the gas is undergoing a chemical reaction. And we're monitoring that chemical reaction with something called an indicator. So we're able to follow and detect gases in air. And this is an important thing, because if you're in a mine, for example, and you want to make sure that there's air to breathe, you could take an indicator along like this and it would tell you how much oxygen is in there and so on. Okay? Now, another gas I just mentioned was carbon dioxide. And so we're going to have, this is what we're using for carbon dioxide, right?
This is going to be for the Allen 2 to make dryers.
Carbon dioxide.
This one, I think. Are you doing the candle one?
Sure, we'll start off with the candle. Except I need the carbon dioxide. I need the vinegar and baking soda.
Yeah, it's right there at the end of the table.
Vinegar, also known as acetic acid. Baking soda, also known as sodium carbonate. A fun little trick you can do with these is if you mix these two together and let them eventually evaporate down into a solid, what you'll get is actually sodium acetate trihydrate. If you then take that, put it in a baggie, put it in boiling water, it'll turn back into liquid, which as soon as you touch, will then crystallize and give you some really cool crystals. So that's an experiment that you can have a little bit of fun with at home. Okay, so what I'm going to do is pour some vinegar in here, and since this is a new box of baking soda, I will open it appropriately, and I'm going to pour in some baking, and you notice that we get lots of bubbles. What we're producing there is carbon dioxide. And I can demonstrate that we're producing carbon dioxide by the simple process of taking a match and sticking it in there, and it goes out. Now, that could have been just the wind or the fact that it's still sort of spinning a bit here. So let's try it with a candle, and we'll see what we can do with this candle. We'll see if we can even get the candle to light. Okay, so if I take this candle and stick it into the carbon dioxide, let's try it this way. Let's stick the candle in this way and see what happens. Oh, there it goes. It goes out. Ha! And not only that, but I can't really even light the candle because, well, I've got carbon dioxide in there and it keeps putting out the flame. Right? So the carbon dioxide's rising up. What we can do is have a little bit of fun with that. So we have a pop bottle here, ordinary everyday pop bottle. How much vinegar do we want in here?
I'm going to put 400 mils.
400 mils of vinegar?
Yeah.
Wow.
We're going to blow up this balloon.
Okay.
Did I hit it?
I have no idea. That look right?
There we are. Good.
There we go. So we're going to put about 400 mils of vinegar in there. For those of you trying to keep track at home, that's about 1.75 cups. And we got some baking soda. Why did I have the new one?
That's okay. I bought extra. Okay, so we're going to add the baking soda into this balloon first.
Where's your balloon?
that end of the balloon off first. And then we're going to connect the balloon onto the top of the pop bottle. And we're going to release this into, and you can see that when we combine the baking soda with the vinegar, that the CO2 gas is blowing up the balloon. Oh, got some spillage in there. So we're just gonna
take that off.
So we're gonna take it off, and we're gonna tie off that carbon dioxide gas in here. Okay.
We're going to blow up another balloon.
Okay. Now what we're going to do is we're going to take this balloon with the CO2 in it, and we're going to put it into the liquid nitrogen. And can you see what's happening to the balloon there? It's just starting to collapse.
So, just pull it back up again. You can see that the balloon's got a bit of a shrinking feeling to it. Where's my tools? There we are. There we go. We'll get it nice and shrunk. So again, liquid nitrogen is really, really cold. It's minus 196 degrees Celsius. Carbon dioxide has a sublimation point. The sublimation point is minus 78 degrees Celsius. So right now, the balloon, the interior of the balloon is filled up with solid carbon dioxide. Now, if we open the balloon up real quick, what we can see is the dry ice or solid carbon dioxide from inside of the balloon. And if we're really quick and careful about this, we can actually collect that, put it in a balloon.
Put that in there.
And seal the balloon off, warm it up,
and we'll see that balloon inflate.
and it should blow our balloon up, he says. You gotta love science.
It's starting. It's slow.
Yeah,
but
it's just
going.
it's just being slow about it. Here, you got some hot water here. I'll warm it up just a bit. But you can see that the carbon dioxide that's now going back into being a gas is making the balloons slowly inflate. It is actually really cold. So it's still not warm enough to, I've still got solid in there. Can you hear that?
It's going to take a little longer.
Yeah. So it's just slowly coming along. We're going to tie that off because otherwise it's just going to take too long. And we'll let it blow itself up. That's not our explosion, by the way. That's just physically blowing itself up. Okay. There you go. So let's try the same thing, only with air. Remember we said that air is 80% nitrogen, 20% oxygen. Well, it turns out that oxygen and nitrogen have roughly the same boiling point. That is, they turn from a gas to liquid at roughly the same temperature. So if I take my balloon filled with air and stick it in there, it should do the same thing. That is, it should get a very, very much a sort of shrinking feeling, shall we say. And if I pull out my tongs and stick it under, we can actually make it go all the way down to being totally flat. So our balloon has, how should we put it, suffered a bit of a collapse or shrinking sensation, right? And the fun part is that if you just let it sit there, it will actually reinflate all by its little old lonesome. Except in this case, my tongs actually poked a hole in my balloon. So much for the balloon. You gotta love science. Like I said, it works great most of the time. So we got some things we're gonna play with here. Let's just clean this up a little bit. So I'm passing stuff off to Beth over here. What else do we have to play with? Oh. How many of you guys like bananas? Everybody like bananas? Everybody make a banana smile? No? You've never made a banana smile? Nobody here has made a banana smile. Somebody online must have made a banana smile. Yes? Somebody send us a banana smile. I just put my banana in liquid nitrogen. Tomatoes. Beautiful tomato. Nice juicy tomato. Into the liquid nitrogen it goes. My evil assistant tied a knot in his bag, so I'm going to have to rip it open. Broccoli. Everybody a big fan of broccoli?
Oh, I love it.
We'll put that in the liquid nitrogen too.
Careful of your foot there.
Oh, yeah. Flowers are beautiful, aren't they? People like flowers. And, you know, like if you take a carnation or something like that, it's a nice, soft, gentle little flower, very beautiful looking. If you stick it in liquid nitrogen, it sort of has a little bit of a problem. Because when you stick it in liquid nitrogen, all the petals get really hard. When you take it out of the liquid nitrogen, well, you can just smash it to pieces.
My poor flower.
Your poor flower.
I'm just going to take that home with me, Todd.
Let's try the yellow one. It's a daisy. So all we're really doing here is liquid nitrogen allows us to freeze the water content of the flowers really quickly. And as a consequence, the flowers essentially become ice, and we can shatter them very, very easily using the tongs or whatever. This, by the way, is liquid nitrogen. If you didn't know it was liquid nitrogen, it sort of pours and looks a lot like water. It's not. It's minus 196 degrees Celsius, which makes it very, very cold. We can do some other fun things with liquid nitrogen. For example, in an ordinary tea kettle. Now, I'm going to need you to just press down on that for a second.
No problem.
And let's see how we're going to do this. We're going to do this way. You don't need to put much in there.
Now it's going.
Okay, and if you let go of that. So it sounds like the kettle's boiling. What you're really hearing is the gas inside there. The liquid nitrogen is turning back into gas, and as it escapes, it comes out of the little whistling hole, and so it's like the steam of a steam kettle. You guys can hear that, right? Okay.
Now it's whining.
And if you're really careful, you could actually play a tune with it.
Oh, Danny boy.
Yeah, we're getting rid of that. Anyways, there's a couple other things we can do. What else can we do? We can show you what is called the airlift principle. This is a piece of rubber tubing. It's reasonably flexible. If I stick it into the liquid nitrogen, what'll happen? Well, some of the liquid nitrogen will get inside the tube, and then it'll start to evaporate. And so what it's going to do is it's going to actually push some of the liquid nitrogen up the tube, because as it evaporates, the gas turns from being a liquid, which is very dense, to being a gas which isn't very dense, and sort of expands outwards. The consequence of this is that if I do this right, I should be able to spit liquid nitrogen right at the camera. And you should be able to see the liquid nitrogen coming off the out of the top of it. The tricky part about this is you actually have to have the tube relatively warm, so we got to warm it back up again to make it work a second time, or I could just do the simple thing of just turning it over, and it'll work a second time. And you can see it's nicely spitting out liquid nitrogen. That is called the airlift principle, and it's actually used in industry to move materials around in pipelines and stuff like that. Okay, what do we got in here? We have a banana. How many of you guys like broccoli? Who here likes broccoli? You guys like broccoli?
I love broccoli.
For those of you who like broccoli, I now have broccoli pieces.
Oh my goodness.
By the way, this is really a great way to make broccoli for like a stir fry or something like that, because now you got all these nice little pieces. You don't have to chop it up. There's no knives involved. It's very easy, right? What about our banana? Come on, pass me your glove, please.
Yeah.
I'm putting on a safety glove here just because I'm going to actually physically grab the banana out of the container. And again, our banana looks pretty good. It's minding its own little business until you come along and you hit it on something hard, like this guy, and then it starts to break into pieces that are all over the place. And you can shatter the banana into little fractions, no problem. Now, the interesting thing about this is that we've actually made the banana age by freezing it. It will turn very quickly. Indeed, as soon as it thaws, it'll turn into that sort of, you know, like when you get a banana and it's been sitting on your counter for too long and it turns black on the outside and the inside sort of gooey and mucky. That's what these will thaw out to. And the reason behind that is because every time I freeze something like this, all the little cells inside of the banana all get their membranes blown apart. So the content of the cell sort of explodes outwards and the skin of the cells gets ruptured. And so the bananas now, all the contents of the cells are sort of everywhere. And that's what happens when a banana gets old. We can show this a little bit differently with a tomato. And you remember I put in a nice big huge tomato? Well, the tomato actually doesn't even survive the freezing process as one piece. You saw that the banana was still in one piece when I pulled it out. The tomato isn't. And the reason behind this is that the tomato is filled up with a lot of water and then it has a very, very thin membrane about it. And so as this water freezes, it expands. We all know that water is, ice floats. The reason ice floats is because it's less dense than water. It's got a bigger volume. And so as the water inside the tomato turns to ice, it expands outwards. And it pushes on the banana and or on the membrane of this tomato and basically pushes it apart. So that we have now a glove that won't go on my hand, but we have two pieces of tomato. And they fit together. I mean, you can put them back together again. And sure, I can smash them. It doesn't smash very well because this is fairly tough. It's solid ice at this point. But the reason that I've always done and used tomatoes for this part of this demonstration is because there's lots of people who tell you that you can freeze human bodies. Our bodies, the cells in our body are like this tomato. And if you were to freeze a cell in your body, it does pretty much the same thing that this tomato does. It shatters into pieces. And so you can't freeze a whole body. You can freeze single cells, but it's really, really difficult to actually freeze a whole human body. It'd be nice if we could freeze people and we could, you know, save them for later or something like that. But in reality, you end up looking, well, like the tomato. It's gone. Okay. What else do we have to do? We're going to play with this guy.
Yeah.
We're going to try this demonstration. This sometimes works and it sometimes doesn't work. So we'll see how it goes today. It might just be misbehaving. It might behave. We'll find out shortly. So this is an ordinary ping pong ball. I'm going to take my ordinary ping pong ball and I'm going to stick it in liquid nitrogen. And I'm going to stand here for a moment and let it do its business. It's gotten nice and cold. tongs are getting nice and cold. But hopefully it's doing what it's supposed to do, which is not collapsing, unlike the balloons. It's just getting really cold, and what it's actually doing, the ping pong ball has a little tiny hole in it, and what's supposed to be happening is that it's supposed to be getting some liquid nitrogen inside. And if I drop it in here, that liquid nitrogen now will warm up, and as it warms up, it's going to come back out of the hole, and if this works, we're going to get a stream of gas coming out of the ping pong ball, and as the stream of gas comes out of the ping pong ball, it's going to act like a little jet engine and cause the ping pong ball to go whizzing around inside the container. And that's the beauty of science, because sometimes science just doesn't, oh, it's starting. Science doesn't do what it's supposed to do, or at least not the way it's supposed to do it. I definitely have liquid nitrogen in there. It's running all over the bottom of the container. Okay, that experiment didn't work.
We helped science out there.
That's why you do experiments, because one work, sometimes they don't.
So we can do the
Okay.
other candle, and then we can do the hot water.
Beth wants to do something. She's been dying to do this for a while.
No, I haven't.
So, you want to put on your safety shield?
I will, yes.
Here's the gloves.
You're gonna get me gloved up?
Yep.
Okay.
Do you remember we put out a candle using carbon dioxide? This is the candle. Here you go.
Oh, okay. Thanks.
We got the candle?
Yeah, I got it.
Okay. Now remember, you can't try and stick it in there, because if it explodes, I want to be far away. Okay? So wait until I tell you you can stick it in there.
Okay.
Okay?
Okay, I'll do my best.
There you go. Okay.
Should I or should I not?
How many people, how many of you guys think that you should put the candle in liquid nitrogen?
Should I?
Okay,
Okay.
I'm gonna hold it. Just stand back a little further. Just in case.
You're giving me concern, Todd. Okay, I'm gonna go for it. I'm gonna go for it. Oh, come on, that's anticlimactic.
Oh, it didn't blow up this time.
The flame went out.
That's a good thing it didn't blow up this time. We wouldn't really want you to blow up, Beth. On the other hand, we really wouldn't want me to blow up. Okay, so as a final thing here, what we're going to do is a very simple little demonstration for you. I have in my hand a beaker filled with hot water. And what happens if I put hot water into really cold liquid nitrogen? Anybody want to guess? Hot water, cold liquid nitrogen, put them together, and we get
Whoa.
a steaming mass of stuff. Essentially, the hot water is now producing a cloud of smoke. It's not smoke, it's actually water vapor that's condensing, so you're getting little ice crystals. We're making clouds. And you might have noticed it was a bit of a sort of a foofero type of cloud, sort of jumped a bit. What Beth and I are going to do is behind me, you'll see way out here, there we go, we can point to it, is a giant garbage can. We're going to go out and we're going to put a pop bottle filled with liquid nitrogen in the water in that garbage can, and we'll see what happens. Okay? So we're going to go over there. I'm going to yell. You might not hear me very well, but Tess will provide some audio commentary, and away we go. what we're doing here is I'm just taking the lid off the garbage can, or the pop bottle. I'm going to hold the funnel in place, and Beth is very carefully, avoiding my fingers, going to pour some liquid nitrogen into the funnel.
If you didn't hear that, the liquid nitrogen is going into the funnel, into the pop bottle.
And we're going to fill up the pop bottle. Okay, so I'm going to give the funnel and my gloves to Beth. I'm doing this gloveless. There are no gloves here. I have to take the gloves off so I can actually screw on the pop bottle. And she gets to walk away.
That's our deal.
Okay, so I'm going to screw the lid on the pop bottle. I'm going to drop it in the garbage can, and then I get to walk away. Okay, so what's happening inside there is that our liquid nitrogen is getting warm. There's water in the garbage can. And we're going to finish with a boom.
Oh, that's cool.
And hopefully everybody can see that. So thank you very much for paying attention. That's what is called a chemistry magic show. And as promised, we finished the whole summer with a boom. Thank you very much for your time.
Awesome, thank you. We still have a couple of questions for you, but yeah, I think you get a round of applause for that. That was awesome. So we have a couple of camper questions. Some of the kids in our clubs wanted to ask you a couple things. So
Sure.
Henry wants to know something related to this. What makes the biggest explosion, and why does it make an explosion?
Well, the biggest explosion was the Big Bang that started the entire universe in the first place. And nobody knows why that happened. But if you're talking about on Earth, it really comes back to a question of what are you using to make the explosion with, and how much. So for example, if you were to take a nuclear bomb, you can make ones that are 10 kilotons, you can make them 100 kilotons, you can make them 1,000 kilotons or a megaton. There's actually nuclear bombs that are multiple millions of tons of explosives. And what they use there is a ton of TNT as a comparison. So the same way you could do it is you could pile a ton of, or a million tons of TNT together, and you could blow it up at the same time, and you would get an explosion as big as a nuclear explosion. So it really is a question of not so much what makes the biggest explosion, is how much material do you want to put in to make an explosion. Okay? But in terms of just sort of repetitive explosion, some of the worst explosions are actually not things like nuclear explosions, but there's a couple of compounds that you can make that go off really rapidly. So what you're also looking at, this one, because we do it in water, the sound wave goes boom, and it sort of does this sort of, it goes up and it comes down. And yes, it's loud, and yes, this is a really short time span, so it's a really loud sort of percussive noise. But if I didn't put the water on there, instead of going boom, it would go crack. And it would be like, you know, when a lightning strike happens right over top of your house, and you get that really sharp thunder, that's the sort of noise that it would make. And in fact, it actually would hurt everybody's ears. So it really depends on what you're playing, what you're doing when you talk about explosions, right? You can make big sort of boomy ones, you can make very sharp ones, but it really has a lot to do with how much you're using.
Okay, awesome. Ariane wants to know, when you do a chemical reaction to make an explosion, is it always carbon dioxide that's released, or what are some other stuff that is released?
No, it depends on what you're using. For example, a nuclear explosion releases radioactive clouds of atoms. If you're blowing up dynamite, it's carbon dioxide, water, and nitrogen, and nitric oxides that get released. If you were to do one with nitrogen triiodide, it's nitrogen and iodine that get released. So it comes back to what is the chemical constituents, what atoms are there, what elements have you built the material that you're exploding out of. And there are lots of things. This one here, that we just did, there was no carbon dioxide released. That was all water vapor and nitrogen being released. So there was no carbon dioxide involved at all.
Okay, awesome. We have another question here. It's a little off topic, but Ariane also wants to know, how come when you place magnets together at the same poles, they don't stick?
The reason is because of the way the force lines interact. This is really a physics question, but essentially, if you look at the force lines, how to explain this? The way a chemist would explain this is inside of every atom there's electrons, and the electrons spin. So they go round and round. Well, if I'm spinning this candle, you can see right now I'm spinning it anti-clockwise. I could also spin it clockwise, right? And it turns out that electrons, in order to pair up, have to be spinning in a way that if this guy's spinning clockwise, this guy has to be spinning anti-clockwise. That way they can meet each other, right? And they can join. And you can imagine if you take these two candles and I spin them around, this guy is spinning this way, this one's spinning this way, and that allows them to actually spin together. Now, if I take the same two electrons and I have this one spinning, for the sake of argument, I'm going to spin it this way, and I spin this one this way, now they won't fit together because they're rubbing on each other. And this guy's wanting to go this way, and this guy's wanting to go this way, and they fall off of each other. So if you can imagine inside of all of the materials that are made of magnets, there are electrons, and those little electrons are all spinning, and if those electrons spin in a way that allows them to pair up, then you get the attraction. And if they're spinning in a way that doesn't allow them to pair up, then they don't attract. The south end of a magnet is the case. A south and a south interaction is where they're spinning opposite. A north-south is where they're spinning in the same direction, because this guy's spinning left-handed, this guy's spinning right-handed. Make sense? Everybody here is nodding, so hopefully you online, that makes sense to everybody out there.
Awesome, thank you. And we have one more question for you. So what do you use chemistry for in your job? Do you make anything with it?
Yeah, I make dinner every night. Chemistry is everywhere. You use chemistry every day. I'm actually an inorganic chemist, and my interests right now are in what happens when you put things like chromium and metals into soils and how it affects the organisms inside the soils. So it's more of an environmental chemistry aspect. But my PhD, I was making compounds. I made palladium macrocycles, which were the first palladium macrocycles ever made. And if you want to know about palladium macrocycles, come take first or second year chemistry from me and I'll explain it to you then. Other people make drugs. So pretty much anything, if you've ever had any sort of aspirins or acetaminophen, if you've ever used anything like that, they're made by chemists. If you've used we're in a pandemic, everybody uses sanitizers. The sanitizers are made by chemists. All these things are sort of invented by chemists or discovered by chemists. One of the things that chemists do a lot of is go out and look at what nature's doing and how it does it. And sometimes we can find really good things in nature that allow us to make a compound or extract a compound that will help us. A lot of the antibiotics, for example, come from natural materials that we have extracted the chemicals from. So there's lots of different places in chemistry. You cannot do anything in a day where you do not interact with chemicals in chemistry. Excuse me.
Awesome, thank you. Well, that's it for our questions.
My pleasure, and I hope you all had a good time today. And I'll turn it back over to Tess.
Awesome. That was a great presentation. Thank you two so much. I hope you guys all enjoyed it as much as I did and learned as much as I did too. So thank you so much for volunteering your time, you guys. It was awesome. And thank you to everyone that joined our Ask A Prof lives this summer. We're so happy to have you. And thank you for joining this one. We hope you guys have a good rest of your summer and a good school year.
Bye.
Bye.
Bye.